Hey, what's going on guys? Tanmay here for Simple Snippets. Welcome back to another video tutorial on data structures and algorithms. And today we are going to start off with one of the most important topics under the binary tree topic, which is AVL tree. Now in case if you're new on this channel, in case if you've missed any of the previous tutorials in the DSA course, please check out this playlist. And a quick note, this is a very important topic, so please watch this video till the end without any distractions. Do not pause in between. I highly recommend that you watch this video in one go, start to finish, and keep all the distractions aside. Also do note that to understand AVL tree, you obviously need to understand what is a binary tree, what is a binary search tree, what is balancing, and all these topics we have individually covered in detail in this DSA course. So again, heads up to those who have missed any of the previous tutorials. Make sure you watch this entire playlist. And with that being said, enough of the introduction, let's start off with AVL tree. So the two important things that we are going to talk about is what exactly is a AVL tree and how does the self-balancing property happen in the AVL tree using the rotations, which of course we'll come to. But first, let's take a brief definition of what is a AVL tree. So AVL tree is a self-balancing binary search tree. So AVL tree is a binary search tree, which means it is also a binary tree, okay? Correct? But it is a special type of binary search tree because it is self-balancing, and we've already discussed what is balancing, where the difference between the heights of left and right subtrees cannot be more than 1 for all the nodes. Now this difference is generally called as balance factor, in short BF, and the BF is always equal to, or it would have the values -1, 0 or 1, okay? So anything beyond -1 or beyond 1, like if the balance factor is 2, 3, 4, then that binary search tree is considered as imbalanced or unbalanced binary search tree and it does not become a AVL tree, okay? So below over here we have 3 examples of a regular binary tree, a binary search tree and AVL tree. Let's take a quick look at it. And in a binary tree, the only thing is that we have a node which has 1, 0 or 2 children, okay? So there is no such rule that smaller values are towards the left, larger values are towards the right. So you can see the values are arranged in a very random manner. So this is the root node n1. So this is the root which has the value 77. Now to the left child, I'll write LF to represent as left child. We have n3 whose value is 87. Now 87 is obviously greater than 77. So you can see that there is no particular way in which these values are arranged. And this is what a generic binary tree looks like. There is no rules of how the data is stored. The only rule is that the structure should have one node with 0, 1 or 2 children. Correct? Not more than 2 children is what the rule is for a binary tree. Okay. So this is first type, which is the very generic binary tree. Now moving on to binary search tree. This is where a binary search tree is also a binary tree with the special property that the value of a particular node is stored in such a way that for that particular node, for example over here, this is the root node, the left child, the LF, will always have value smaller. So you can see 45 is smaller than 87. So the left child will always have the value smaller than the parent node, and the right child, I'll say RC, okay, so this is not LF, this is LC. So RC is right child, which is N7, who has value 91, which is greater than the parent node 87. And this rule is followed by every node. Again, we've extensively talked about binary search tree in separate tutorials, but you can see the only difference over here in binary tree and binary search tree is that all the nodes are exactly the same. So we have N1 over here as the root, but N1 is situated over here with the value 77 in this binary search tree because of this particular arrangement. So we have the same nodes with the same values, and structurally both of them are binary trees only, just that the arrangement is different in a binary search tree. Okay? Now taking this same binary search tree one notch forward, that is one level more with extra condition, this is where we come to the third type, which is AVL tree. So AVL tree is nothing but a self-balancing binary search tree. So it is technically a binary search tree only, just that it is balanced. Now if you observe this binary search tree, which is second one, this is not balanced. How do you calculate or how do you figure out whether it is balanced or not? We've already discussed this in previous tutorial in detail, but just to give you a brief, what you have to do is you have to calculate the height of the left and right subtree and take a subtraction between the two. So for example, for this root node n3, this is the left subtree and this is the right subtree, correct? So height of left subtree is the longest path from the root node. So for the left subtree n2 is the root node, correct? And the longest path is from n2 to n1 and n1 to n6, or n2 to n1 and n1 to n5. In both cases we have 1 and 2. So left subtree height is 2 and the right subtree, this is the root node, correct? Does it have any children? No. So in that case the height is going to be 0. So over here the difference between left subtree and right subtree is equal to 2 minus 0, which is equal to 2. So now since the balance factor, so this is basically what we did is we calculated the balance factor for this binary search tree, and of course this has to be done for every single node, but over here we got the first value itself as unbalanced because 2 is not in this set. 2 is greater than 1 and hence we can say that this is unbalanced or imbalanced. Hence this binary search tree cannot be a AVL tree. Okay. Now taking this forward, as I mentioned, this is the third kind of tree, which is AVL tree, and these are the same nodes but they are arranged in a different way. And over here if you calculate the balance factor, so just by looking at it, this is the left subtree, this is the right subtree for this particular root, and you can see the height of left subtree is equal to 1 because we have only one hop or one edge which is on the longest path starting from this root node till the leaf node. And for the right subtree also the height is equal to 1 starting from n3 to n7 or n3 to n6. Neither of them are the longest paths, so they can be considered the same, and there is only one edge between, so height is 1. Now if you take LST minus RST over here, it is going to be 1 minus 1 and it is going to be equal to 0. So 0 is lying in this range, that is, it is exactly balanced. And of course, as I mentioned, this has to be calculated for every node. So right now we just calculated the balance factor for the root node n1. Similarly, if you just take this particular node, this is the left subtree and this is the right subtree for node n2, and again the height of left subtree is over here is 0, over here is also 0. If you take a subtraction you'll get 0, which is again coming in the range of the balance factor, which is valid for AVL tree. If you do this for all the different nodes, you will get values which are ranging from -1, 0 and 1 only, and hence you can say that this is a valid AVL tree. Okay, alright. So all in all, theoretically, and the definition of AVL tree is that AVL tree is a self-balancing binary search tree where the balance factor will never go beyond 1 or below -1. And one last thing that I want to state, that is every binary search tree is a binary tree. Every AVL tree is also a binary search tree. However, the reverse is not always true. So not every binary tree can be considered as binary search tree, and not every binary search tree can be considered as AVL tree. So keep that in mind. I'll just draw a Venn diagram also. You can see that the AVL tree is the smallest set. Every AVL tree is a binary search tree. So that's the larger set, and every binary search tree is a binary tree. So the reverse is not true. Okay. Alright, so with this basic understanding of what is a AVL tree, the next obvious question that arises in the mind is, how does this self-balancing happen, right? So of course there has to be some way in which this binary search tree becomes this AVL tree, right? If you do some arrangement or rearrangement of these nodes, we can get this structure. So how do you achieve this? So this is where the self-balancing process happens, and that is happening by performing rotations. And now let's look at that self-balancing process of rotations. Okay, so as I mentioned, to maintain the balance in AVL tree, we do some rebalancing or self-balancing. And when I say self-balancing, obviously the binary search tree is not gonna balance itself by default. We will have to do some process to do that balancing. And when it comes to the practical and implementation side, we will have to write some code to do the balancing or rebalancing. So this is done by using the concept of rotations. Okay. Now let me demonstrate these different rotations, and let's assume that you want to insert 3 nodes in a AVL tree. Okay, you want to create a AVL tree and you want to insert 10, 20 and 30. Now there are 6 ways in which you can insert these values. I am showing 4 because the other 2 are the order in which the insertion happens. The tree is already balanced. Okay, so we'll talk about the remaining 2, but the order in which the insertion can happen is we have 6 different ways, and out of them 4 are needing the concept of rotations. So that is what is depicted over here. So these are the 4 different ways in which you can insert. So you can either insert 30, 20, 10, or you can insert 10, 20, 30, or you can insert 30, 10, 20, or you can insert 10, 30 and 20. So there are 2 more ways, but as I mentioned, we'll discuss them later. Let's talk about these 4 different ways, and let's try to first create a binary search tree using these insertions. Okay, so let's talk about the first case. So first you insert 30, right? Okay, so we just created a node 30. Let's name it N1, and of course this is going to be the root node, correct? Alright, so the next node that we want to insert is 20. Now as I mentioned, we are constructing a binary search tree, and out of the binary search tree we also want to do rotations and get the AVL tree. So when you're creating a binary search tree, remember the placement of these values matter. So remember 20 is smaller than 30. So in that case 20 will be the left child of N1, correct? So this is how it would go to the left. So let's create a node over here. So this is 20, correct? So this is the left child. Let's name it N2. Similarly, again when we insert 10, again that would go to the left. Let's write 10 and let's name it N3. Okay. Alright. So this is a proper binary search tree, even though it looks like singly linked list. That is because we do not have right child for every node. We only have left child for every node. And just by looking at this binary search tree, you can say that this is imbalanced, right? How? If you just calculate the balance factor for this particular node, this entire part is the left subtree, LST, correct? And there is literally no node in the right subtree, correct? So for this left subtree, we have root as N2, and from N2 to N3 we have one edge. So the height of left subtree is equal to 1. We don't calculate or we don't count this edge, okay? The edge between N1 and N2 is not counted because for the left subtree, N2 is the root. And starting from the root, we have to go to the longest path till we find the leaf node to calculate the height. We've already discussed how to calculate height. I hope you know that. So left subtree height is equal to 1. The right subtree height is going to be equal to -1, and that is because we literally do not have any node. If we had any node, the height would be 0. If we had further children, the height would be 1. But right now, since we do not have any node in a tree where there is literally no node, the height is considered as -1. And now if you take the subtraction of LST minus RST, you'll get 1 minus -1. So this will result in minus will become plus. So you'll get 2. And remember, the balance factor BF has to be equal to -1, 0 or 1. Anything apart from that, it would mean that your binary search tree is imbalanced. So hence you can say that this binary search tree is imbalanced, correct? So now the next question arises, how to balance this? And as I mentioned, we are doing rebalancing and we are going to do some rotations. So this is where we will rotate or we will change the orientation of this binary search tree in such a way that you will do a right rotation over here. Okay, so what do I mean by right rotation? So let's say if you take this node N2 at the place of N1, and if you bring this N1 down and make N2 as the new root, the structure would look something like this, right? You can see. And now if you see that this structure is a binary search tree because it is following the rule where for every node the left child is smaller. So for N2 we have left child N3 which is 10, so 10 is smaller than 20. For N2 which now has become the root node, we have N1 on the right child and 30 is greater than 20. So yes, it is a binary search tree and it is also balanced because now if you calculate the height, you'll get the balance factor as 0. So what we did over here is we shifted n2 to the top towards the right and we shifted n1 below, and this is what is called as a right rotation. Okay? So when you shift a particular node towards the right in this direction, you can see it is a clockwise direction, correct? So n2 went to the top and n1 was pulled down, as if you have a point over here which is acting as the pivot point. So you're taking n2 to the top and you're bringing n1 to the bottom, and this is known as a right rotation. Let me write over here RIGHT, right rotation. Now this scenario is called as left imbalance because you can see that the binary search tree was more heavy or having more nodes towards the left. So it's also known as left imbalance or left imbalance sometimes. And in such scenarios you do right rotation. Okay? Alright. So this is the first type of rotation. Let's see the scenario 2, where the order of insertion is 10, 20 and 30. So first you insert 10. Let's call it n1. Then you are inserting 20. So 20 is greater than n1. So it would be the right child of n1. So you get 20. Let's call it n2. And then you want to insert 30. So 30 is again going to be the right child of n2 because 30 is greater than 20. Let's call it n3. So again you can see that this is a binary search tree. Yes. But is it balanced? No. Again, if you calculate the left and right subtree heights and do a subtraction, you'll get the answer of 2, which is basically not valid. The balance factor has to be -1, 0 or 1, correct? So this is again an imbalanced case, and this time the imbalance is happening towards the right, so this is a right imbalance. Now in this scenario what you do is you do a rotation towards the left. So again, if I were to take this node and put it over here and take this root node n1 and pull it down, you can see we are going in a leftwards way, right, in the anti-clockwise direction. So this diagram or this structure will now be changed to something like this, and again you can see now this is again balanced, but this time what we did is we did a left rotation. So let's write left over here. So when you have a right imbalanced tree, you do a left rotation and then you get a balanced binary search tree, and in both these cases now this can also be considered as a AVL tree. Okay, so this is a AVL tree and this is also a AVL tree. So from a binary search tree, so this was a binary search tree but it was imbalanced, we did the balancing, we did the right rotation, we got a AVL tree. Again, this was a binary search tree but it was imbalanced, we did a left rotation and we got a AVL tree. Alright, so these two scenarios were pretty straightforward. We just had to do one single rotation and we got the AVL tree. Let's see scenario 3. Okay, so here we are inserting 30, 10 and 20. So let's insert 30. Then we are inserting 10. So 10 is smaller than 30, so it has to be the left child. So I'll write 10. I'll draw the circles later. Let me do 10 over here. And then we are inserting 20. So 20 is smaller than 30. Yes. So it will go to the left. But 20 is greater than 10. So it will be the right child of 10. So 20 has to be somewhere over here. Correct? Alright. Let me do the circles. So this is N1, N2 and N3. So from N1 we are going to N2, from N2 we are going to N3. Alright. So is this a binary search tree? Yes. And is it imbalanced? Yes, it is still imbalanced because these two parts or these two nodes are still to the left of N1, correct? You can see. Let me just extend it over here. For N1, we have two nodes onto the left. We don't have anything to the right, which means that it is imbalanced, and if you calculate the left subtree and right subtree height, you're gonna get 2. But you can see this is a very weird structure. It is not exactly left imbalanced or right imbalanced. In fact, it is a combination of both. So this scenario is usually called as left-right imbalance. That's because the second node N2 is towards the left and the third node N3 is towards the right of N2, not N1. Okay? So they are still one-sided onto the left, but they are not like all of them are towards the left. That's why this is a very tricky scenario, correct? Alright. So how do you balance this? So in this scenario, can I do a right rotation directly? Can I take N2 and move it towards N1 and get down N1 over here? Let's try that. So if I do the right rotation, so this is how right rotation is done over here. You can see this was the scenario 1. I did a right rotation and after that I'm getting this result. If you observe this, this is a balanced binary tree. However, is it a binary search tree? So for a binary search tree, for this root node N2, the left side or the left child has to be smaller, but N3 is 20, which is greater than 10. So you can see this is invalid and this is not a binary search tree. And if it is not a binary search tree, obviously it cannot be a AVL tree. So this simple right rotation is not working. Alright, let me erase this. Can we do a simple left rotation? Is there any way we can do left rotation? How do you do a left rotation on this? You can't do a direct left rotation because you cannot put N3 directly at the place of N1 because there is N2 in between. So left rotation is out of the question. So this is where we have to do a left and right 2 times rotation. But for that, the first left rotation has to happen between N3 and N2. So you'll get N3 at the place of N2 and N2 at the place of N3. So you'll perform left rotation, and after performing left rotation, this is how our binary search tree would look like. Let me quickly draw it. Alright, so this is how the first left rotation that we did on N3 and N2 resulted into a left imbalanced binary search tree. So is this a binary search tree? Yes, because N1 is 30, its left child N3 is 20, which is smaller than 30. Again for N3 we have a child which is a left child 10. So 10 is obviously smaller than 20. So yes, this is a binary search tree. But is it imbalanced? Yes, because we don't have anything towards the right. So obviously it is imbalanced if you calculate the heights. And now if you observe, this binary search tree looks pretty similar like the first case where we are getting 30, 20 and 10. So now you can do a right rotation, and when you do a right rotation, you can take N3 at the place of N1 and you can bring N1 down. So now you do a right rotation and this is what the result that you get. So after the right rotation, you are getting a proper balanced binary search tree. N3 is 20, to the left is 10, which is smaller than N3, and to the right is 30, 30 is smaller than 20. So this is a binary search tree as well as it is balanced. So yes, this can be considered as a AVL tree, correct? Alright, so you can see this required 2 rotations. So it is usually termed as left right. I'll write LF in short, LF rotation. So I hope you understood why we had to do 2 different rotations, because we could not directly take N3 at the top using one single right rotation because N2 was in between. So we first swapped, or we first did a left rotation between N3 and N2, and then we got this left imbalanced binary search tree, and then we did a swap between N3 and N1. So the rotation will happen between 2 nodes only and not directly between the third node if there is one node in between. So that's why we had to do 2 different or 2 separate rotations, one left and then right, to get this AVL tree. Okay. So similar to this case, we have the fourth case where the order of insertion is 10, 30 and 20. So let's draw the binary search tree for this. So we have 10, then we have 30, and then we have 20. So this is N1, this is N2, and this is N3. N2 is the right child of N1 and N3 is the left child of N2. So N3 is still at the right of N1 because N3 is greater than N1 obviously, but N3 is smaller than N2. So again you can see this is not directly a right imbalanced binary search tree, or it is not a left imbalanced, but it is a combination of both. So hence it is usually called as a right left imbalance. Ignore my handwriting, it pretty much sucks. But yeah, again, this is not straightforward and you cannot get the AVL tree with one single rotation just like the case 3. So in this case what we will do is we will first do a right rotation between n3 and n2. So we'll take n3 to the top and bring n2 down. So that would be a right rotation, and that should result in something like this. And this scenario looks pretty much same like the second scenario, which is a right imbalanced tree, correct? Is this a binary search tree? Yes, because the values are arranged in descending order towards the right. So n1 has 10 and its child n3 is 20, hence it is the right child of n1. Then we have n2 whose value is 30, hence 30 is the right child of 20. So this is a binary search tree, yes, but it is imbalanced because we do not have anything towards the left, correct? We have everything towards the right. So this is a valid binary search tree, but it is still not a AVL tree. So one more rotation is supposed to be done, and this is where we have to do one left rotation now. So for the left rotation, we will take n3 towards the left and move n1 towards the bottom, towards the left side. So this is a anti-clockwise rotation or left rotation, and after this we should be getting a proper balanced binary search tree, which looks something like this. Okay, so you can see this is a balanced binary search tree, and hence we can call it a proper AVL tree. So this kind of rotation is termed as, again, what we did first, we did right. So R, that is right, then we have left and rotation. Okay, so these are the four basic types of rotations which are done on imbalanced binary search trees to perform the balancing or rebalancing and make the binary search tree a AVL tree. Now, as I mentioned, there are still two more scenarios in which values can be inserted using these 30, 20 and 10. And what are those? Let me just show it to you. If you insert 20, 30 and 10, you will get a balanced binary search tree, hence it is a AVL tree. If you insert 20, 10 and 30, again you are gonna get a balanced binary search tree, hence it is gonna be an AVL tree, and that is the reason why I did not show you these two scenarios. You can see them on the screen. If the order is gonna be 20, 30 and 10 or 20, 10 and 30, in both cases we are gonna result with the same structure, which is gonna be balanced binary search tree, hence it is directly a AVL tree, and that's why it does not require any rotations. So that is the reason why we considered these four scenarios. Alright, so this was AVL tree and the different rotations that are used to do the rebalancing in case if a binary search tree becomes imbalanced. And remember, AVL tree is nothing but a balanced binary search tree, so all the functions, all the operations that happen in a binary search tree will also happen similarly in an AVL tree. However, whenever you insert new values or delete existing nodes from a binary search tree, there are chances that that binary search tree will become imbalanced, correct? So, for example, this is a balanced binary search tree, which is a AVL tree. In case if I delete this node and add a new node, let's say the value is 5, and add a new node n5, it will go to the left. So I deleted one node and added a new node, but now this binary search tree has become imbalanced. It is still a binary search tree, but it is not a AVL tree now because it is imbalanced. So every time you insert a new node or delete an existing node from a AVL tree, chances are that it is becoming an imbalanced binary search tree. And that is why whenever you do insertion and deletion in an AVL tree, the operation is similar to binary search tree, but there is one extra step every time you insert or delete, and that is you have to check the balance factor. You have to calculate the height and do the subtraction and see if the balance factor is not going beyond 1 or below -1, right? So that is something that you have to do programmatically and practically, which we will see in further videos. In this video, we just wanted to discuss the different rotations and discuss the AVL tree data structure and how it is an extension of binary search tree itself. And lastly, answering the question of why AVL tree is because an imbalanced binary search tree will have a lower performance compared to AVL tree. Now we've talked about performance when it comes to the time complexity of an imbalanced binary search tree versus a balanced binary search tree in previous tutorials. We want a very high performance. When I say high performance, we want the time complexity to follow the curve of log n and not become the time complexity of a linear time, that is O of n. And to maintain that high performance and high time efficiency, a AVL tree is much more better than a regular binary search tree, which may become imbalanced, right? So that is the reason why AVL tree is very, very important, and it is practically used in many applications as well. And I hope now you know what is AVL tree and what are the different rotations. Okay, so in further videos we will see more examples on AVL tree and do some more complex balancing also. And as we proceed, we will also implement this programmatically. So if you are new on this channel, please subscribe, turn on the notifications. And if you like this video, if you understood the concept of AVL tree, let me know in the comments. Give this video a like. Share this video with your friends as well. It is very important. And I'll see you guys in the next one. Peace.